more engineering side, so I use the sensors quite a lot. That the functionality to convert that voltage into the corresponding temperature. Next one, please. So this is the example I just picked up from the RS online. This is one of the temperature sensor, which is actually, we can't call it nanomaterial, but it's a micro material, maybe just between normal millimeter to micrometer size material. And the data sheet gives you some values, temperature values, and corresponding ratio between RT over R25. RT is the current the resistance at current point. R25 is the resistance at 25 degrees, which is the room temperature. So if you go to room 25 temperature, you can see. Can you go to 25 temperature 25 degrees Celsius? Can you move down, please, on the first column? No, first column 25 degrees down. Yeah, you can see is 1. The next one is 1. Yeah, that means because the temperature, the resistance of temperature at that point 25 degrees and the resistance at 25 same, so they're 1. So when the temperature increases, you can see the ratios goes down, and resistance decreases, ratio goes up. From the ratio, we can create a function. We can use a mathematical model to create a function between temperature and the ratio, and that function can be built into the microcontroller to actually detect, actually calculate the actual temperature. Next slide, please. There's so many NTC in the market, right? There are glass thermistor, precision NTC thermistor. So they're going towards nanomaterial based thermistors, flexible NTC thermistor, surface mount chip thermistors, PCB through hole thermistors. And so there are so many thermistors, and as an engineer, you should decide which one you want. That depends on the application, right? So the applications can be determined, or the choice of the thermistor can be determined, or sensor can determine the size. Do we want a miniature? Do you want surface mount? We need a very tiny, which is like a nano scale. And accuracy. Accuracy also important, because depending on the accuracy, we can, if you talk about nanoscale devices, accuracy will be very high. So that is where we talk about nano sensors. And reliable. So it should give you reliable results. You keep on repeating reliable same results again and again for same temperature. So the reliability is very important. Resolution and accuracy quite linked together. And durability it should last for longer time, right? And the cost, of course, cost is the final thing. So these are simple things we consider when we design a sensor. Next slide, please. So I just researched or looked up some of the papers. I understand there are so much of research still going on in nanomaterial-based thermistors. So I'm just going to pick up 2 example papers I found, recent papers found, where they use different materials to improve the NTC, the thermistors' accuracy. Yeah. Okay. Next slide, please. Right. So if now we talk about nano sensors, so sensors is nowadays, because this course is more about nano sensors. So I need to touch on the nano sensors. So nano sensor again measures the physical properties, but with the nano sensitivity compared to the micro sensitivity. So nano sensitivity, we are talking about temperature in terms of micro Celsius or nano Celsius differences, because that is very important when you are applying a sensors in biomedical applications, in very sensitive applications. So they are very high efficient, multiplex functioning, so you can have a different functionality within a single sensor, high flexibility sensing applications. On almost every industry nowadays try to have a nano sensors in their application, in their products. So next one, please. Right. So one of the applications we had, one of the research work we had in Brunel University with my PhD student is a Electro graphene coated ECG sensor. So graphene is a nanomaterial. We'll talk about that in a minute. So as you know, ECG is a sensor which detects the electrical activity from the heartbeat, right? So when each time heart beats, we all know we went to go to the hospital, and they put some leads and some wires going around everywhere, and they see some kind of on a screen. They see some kind of graphs, signals going up and down. That's ECG. So nowadays, we need to have ECG for different applications, right? So in a hospital, it's fully rested. So they make you to sit or lie down on a firm manner, right? They don't want you to move around because they can get the best signals. But ambulatory. So if you are going in ambulance, they have a probably better sensor, so that they can measure your heartbeat or your heart activity on a moving vehicle. So continuous monitoring, that is becoming more and more popular now, because when you are in patient, there are so many instances patient need to be monitored continuously. So that means you need to do your work activities like a walking, you're moving around, cooking or writing, whatever. Still, you should be able to detect ECG signals in a good quality signal. So that is becoming more and more challenging. And long-term monitoring. So you should have it fixed with you on a wearable manner. So it shouldn't be affect your daily life, and also you can keep monitoring for longer days, maybe a few days or a week, so that the patients can be monitored in a longer manner. There's so many ECG electrodes. The gel-based is a very basic one. They apply gel on the electrode before they stick onto the body, because to create a good connection between the body and the electrode. Dry is more easy because people don't like gel, but that actually produces the less connection. But nowadays there are so many researchers going on doing some best dry electrodes. And next one is non-contact. So that means the electrode does not touch the skin, but then it's like a capacitive effect. So between the skin and the electrode, we have to create a capacitive effect, and but they are not becoming that popular because of still in a research stage, as I know. And the carbon nanotube, there are some advancements in terms of carbon nanotube based ECGs. You can find more details. The paper I put down on the bottom, that's one of the publications we had with my PhD student. We had some information about the various types of ECG electrodes currently available in the market or in the research. Next slide, right? Yeah, graphene. Graphene. People know graphene is a sort of one of the intervention in 2000s. So it's a 2D material. We can call it nanomaterial. It's a single layer carbon. We call it wonder material with superior electrical and mechanical properties. So many applications being talked about, researched, or it's still going on. A lot of research going on. It could be a biosensor. It could be solar panels. It could be nanoelectronics. And I just picked up this table from another paper written by my student, where you can find the difference between the properties of the DC current density, melting point, mobility, thermal conductivity, mean free path at room temperature. So this actually clearly you can see the last column is graphene. GN means graphene. Silicon, copper, I don't know what's XSWC, and I think carbon nanotube. So you can see the current, the melting point is quite high compared to carbon nanotube. Mobility is also very high, and thermal conductivity is very high as well. And mean free path, how far can travel freely in the free space, is also almost 1 kilometer, 1 nanometer. It can travel without any collision or something. That's what it means. So graphene is is a material, advanced materials for people who are interested. So we also thought we should try graphene for the ECG electrode. Next one, please. As I mentioned, the student who worked on this project was Newman Seelig. He's working at Brunel University as not Brunel, as Oxford University as a postdoctoral researcher. So it's a dry electrode, and for improved and stable operation. So it's a dry electrode always preferred over the gel-based electrode. Signal to noise ratio was improved by graphene coating by 8%. The impedance of the electrode was improved by 78%. So the impedance is the resistance between the electrode when it's connected to the skin. We can measure the resistance between the 2 points within the electrode and see how much it's improved. Smooth skin electrode contact. So better accuracy and the stable detection allowed for continuous monitoring. So this is one of the sort of potential suggestion or potential improvement towards the continuous monitoring of ECG signal. Next one, please. Right. So there are, people who are in this world of graphene and nanomaterials. They know how to do how the ECG, so how the graphene is coated. So many methods, which I'm not expert on that. But the one we used, or my student used, is chemical vapor deposition. Obviously, actually, he didn't use it himself. He actually outsourced from the company called 2D Tech. It's a spin-out company from Manchester University, from the staff or from the researchers who actually were part of the graphene group who invented the graphene. So it's a process is explained here in a sort of systematic manner. So copper electrode or copper metal surface is used to create a graphene layer using the chemical vapor deposition and spin coating on top of it. But don't ask me how does it work, because that's not my experience. But this is a process we were given, and wet etching, right, and rinsing create the graphene coat, and then that can be transferred onto the existing electrode, into the graphene. So finally, we have then use a solvent to clean it the top part. Then we have the graphene onto the electrode. Yeah, that's how this is a process. If somebody is interested, probably they can talk to Rama. Probably he will be able to get in touch with me, and then I can get in touch with the company who made that graphene for me. Yeah, next slide, please. So we did some scanning electron microscopic images. Electrode. What happened is we bought a ECG electrode from a company, and then he stripped off, and so he has a silver electrode, and top of that we put a coating. So before the coating we do the SEM image scanning, and the top one shows how they look alike. And once the graphene is coated, we can see there's a difference. Right? The difference is a very very nano structure, and the second one is the bottom one is the graphene coated, top one is the graphene without graphene. So at least it shows the graphene is coated. We can see the graphene is there, and also you can see more smoother. The structure is more smoother. There, it's not 100% smoother, but it's more smoother. So there are some residual points. Of course, when you do the chemical vapor deposition, it won't be perfect. It won't be uniformly distributed, but at least it gets better than without the graphene coating. So next slide, please. Next slide, please. So we have, Kumar probably know much. My previous presenter knows much better than the microscopic facilities or the experimental techniques facilities we have in our Brunel. But I know there is a center called Experimental Technical Center Facility, ETC, where we can have various scanning electroscopes. So these images, the one we showed before, clearly shows there's a coating there, and the coating is more smoother. So smoother coating means you can create a better skin electrode contact. And also graphene covers, you can see the coating done properly. So you can see a lot of coating around the area. Uniform coverage, except few residuals. Yeah, this is one way. This SEM image is one way of showing the coating has took place. Next slide, please. Yeah. So what we did, another thing is, as an engineer, we always want to do some kind of verification with the modeling work or with the theoretical analysis. So we use model console. Console is a multi-physics software which actually allows you to create a model, a three-dimensional model or two-dimensional model, whichever is more suitable for your application. Then we can see how the electrical properties or the physical properties it changes when you run under certain conditions. So in this example, you can see we have a model which actually, let me open mine because we created a skin model where we can put a electrode on top of it. So we put two electrodes just for the sake of modeling, and one of them is reference, that means grounded. Other one you can imagine is grounded. Other one is electrode to measure. So skin model, I think my student found this model from another reference where we have a artery and the splash and this terminology, epidemis, and these are the terminologies used in the model. So these are the different skin condition or different flash condition, and each has got different conductivity, right? So on the table on the right top right shows what are the conductivity used in the model, right? So its conductivity and the relative permittivity is graphene is 1.18 10 to the 9. Ag silver. Silver is actually the one we used the electrode. So the coated electrode, actually the graphene is coated on top of the silver. So that is 61.6 10 to the 6 Siemens per meter, the conductivity, and other three the body parts or the flash parts, which gives you different conductivity values. And what we can see is there are some slight difference. The result shows electrical field norm, right? So electric field when the electrode is connected to a body, and that shows some difference. But are we getting any some sensible understanding at the moment? No, but it can be a good starting point, because this is to get some understanding what actually happening within the body when we have a graphene coated, when we don't have a graphene on top of it. But there's a small difference in terms of electric field, because the conductivity, the graphene is with the graphene we have a slightly better electric field pattern. But at the moment, I'm not saying there's a big significant knowledge we gained, but at least we can do something to model a system on a body. Next slide, please. Right, this is another experiment with the electrode, where a graphene coated electrode and not graphene coated electrode. There are 4 different types of electrode used. One is